Hello everyone, my name is Tarık. In this presentation, I'll talk about our paper Policy Learning for Visually Conditioned Tactile Manipulation. This is a joint work with Professor Taşkın Padır and Professor Robert Platt at Northeastern University. Our main goal in this work is to localize the robotic gripper with respect to an image of the environment to solve manipulation tasks. We achieve this goal by introducing a differentiable Bayes filter that can estimate the position of a gripper using tactile information. Later, we use this Bayes filter to learn contact-rich manipulation policies that can fuse visual and tactile information. In unstructured environments, it is necessary to use visual information to achieve successful manipulation tasks. However, methods that only use visual feedback have several shortcomings. For example, poorly calibrated cameras can lead to low performance due to noisy estimations. Even with a perfect hand-eye calibration, the robots might have kinematic inaccuracies. Finally, due to partial view from visual sensors, it might not be possible to capture the whole information of the environment for solving these tasks. Therefore, it is desired to use a direct information between the robot and the environment. In this case, we can rely on tactile feedback, which provides important information of the robot-environment interaction. Our experimental setup consists of a parallel robotic gripper with active compliance. We have a depth camera that captures a single depth image prior to the interaction with the environment. In our experiment, we consider two scenarios. The first one is a tabletop environment in which we place objects on a table and the gripper moves in a plane parallel to the table while interacting with the objects. There are two sets of objects, a primitive shape set and an arbitrary shape set. Note that due to low stiffness of the gripper, the objects do not move. In the second scenario, we have a drawer and the gripper is trying to open the drawer by placing the fingers on the correct position of the handle. Now we formalize the tactile localization problem. Since we don't have access to the underlying state of the gripper, we formulate this problem as a partially observable Markov decision process. To solve this, we use a discrete Bayes filter. Bayes filters estimate the system state by using a transition model and an observation model. The belief is estimated by taking the prediction and observation updates at every time step. Since the transition and observation models are not known, we learn them from data generated in simulation. To do so, we represent the observation and transition models with neural networks. The state space is defined as the pixel coordinates of the gripper in the image taken before the episodes. We simplify these coordinates by projecting the 3D position of the gripper to the image space. Our observations are a short sequence of hand joint velocities. The actions for the gripper are defined as fixed distances in 4 directions. In the case of the drawer environment, the agent also has an open drawer action. Our problem can be defined as the estimation of the state given the environment image and the tactile observations. We represent the belief as a matrix with the same size of the environment image. The neural network architecture of the Bayes filter has 4 modules, as shown in this figure. The image encoder takes the image of the environment and passes it through 2D convolution layers to produce the feature maps. Similarly, the observation encoder takes the tactile feedback and feed it into 1D convolution layers. The output of these two encoders are then combined and passed through a 2D convolution decoder, which generates the likelihood map. These 3 modules form our observation model. For the transition model, we use a single 2D convolution layer that takes the previous belief and transitions the state to the next belief. The predicted belief and the likelihood map are then multiplied element-wise and normalized to generate the next belief. In this work, we consider 2 control problems. In the first problem, the aim is to localize the gripper's position in minimum number of steps. For the second problem, we want to move the gripper to a desired location in the state space. To investigate these problems, we experiment on 3 tasks: active localization, navigation, and drawer opening. For solving these tasks, we use an actor-critic method called proximal policy optimization. We chose this method due to its robustness to the hyperparameters and sample efficiency. For the active localization problem, we learn a policy that is conditioned on the current belief of the gripper position and the image of the environment. For the navigation problem, we also give a goal state to the policy. In all tasks, we use sparse rewards. The active localization task gets reward of 1 if the predicted belief equals to ground truth state. In the navigation task, reward is 1 if the gripper reaches to the desired state within a threshold. Finally, the drawer task gets a reward of 1 if the drawer is fully open. This figure shows the general framework of our method. At every time step, we estimate the belief using the environment image and the tactile observations. This belief is then fed into the policy network. The policy takes the environment image as input. In the case of navigation and drawer opening tasks, the policy also gets a goal state represented as a one-hot image. We first investigate our method in simulation experiments. We compare our method against two baselines. The first one is using a recurrent layer instead of the belief estimation. This is a common approach for handling partial observability. The second baseline is the point estimate of the belief. This baseline shows the effect of uncertainty estimate from the belief. We train the policies in simulation for all tasks and report the mean reward in this figure. As can be seen from this figure, our method outperforms the baselines and achieves higher success rates in all tasks. We further analyze our method's generalization capabilities. To this end, we train the active localization and navigation tasks using only 4 primitive shaped objects. After the training is completed, we evaluate them on 2 different scenarios. The cluttered scene has the same shapes, but it has 10 objects instead of 4. In the mesh scenario, we consider arbitrary shaped objects that are taken from the 3DNet dataset. For each case, we run 10,000 episodes and report the mean success rate and the mean episode lengths. These results show that our method can work in cluttered scenes and also generalize to novel objects. Finally, we look at the performance of the policies under observation and transition noise. We sample the transition noise from a uniform distribution and sample the observational noise from a normal distribution. The results shown here explains that our proposed method can still perform successfully even under noise. We then transfer the models that are trained in the simulation to the real world. Since we are using depth images and hand-joined velocities, our transfer does not require any domain randomization or fine-tuning with the real-world data. We evaluate the active localization and navigation tasks for 10 episodes using 10 different objects. At each episode, we randomly place an object on the table and start the episode. We found that the active localization was able to solve the task 9 out of 10 times, and the navigation task was able to solve each time. In the following video, we showcase some of the episodes for the navigation tasks. In this video, the left upper image shows the environment, the right upper image is the depth image, the left and the right bottom images are the belief and the likelihood maps, respectively. Similarly, we show the video of the drawer opening tasks. In this work, we presented a method for estimating a gripper pose with respect to the environment image. Moreover, we showed that this estimation method can improve the policy learning for solving contact-rich manipulation tasks. In the future work, we would like to extend our method to be able to estimate the full 6D pose of the gripper. We also want to explore different manipulation tasks. Thank you for your attention and feel free to contact me with your further questions.